Not showing method here.
All right, morning, everybody. Please get set the usual rules. Kindly shut your laptops and your phones. And just to keep yourself from, being attracted by them, turn your phones upside down. And don't forget to sign on to the attendance poll, which is on the slides, right? Yeah. The attendance poll should be 651, right? Okay. All right. I'll give everybody a second for marking your attendance, and let's begin. Today's is a very long lecture. That's its usual 80 minutes, but then I have 290 slides because, yeah, that's this lecture, right? So let me begin. So here's what we have. I'll wait for you guys to shut your laptops. Can you shut it? Yeah, thank you. So here's where we were so far. Get your name tags out, guys, if you can. We saw that MLPs are Boolean function approximators. I mean, the universal function approximators. They can model any odd thing, Boolean functions, classifiers, regressors. They can be trained to approximate these functions through variations of gradient descent. And the kind of models we've seen so far are of this kind: feed-forward multi-layer perceptrons, where information starts at the input layer, and then it progresses sequentially through all the layers of the network till it eventually arrives at the output layer where a decision or a prediction may be made. But now, let me change the problem. Let me say, now, let's consider this model again. And let's consider the problem of trying to recognize a wake-up word. Now, all of you are familiar with the wake-up words. When you use your Alexa, you just call out Alexa or Hey Google or whatever. That's a wake-up word. So if you were to do this naively, then you're going to have your wake-up word, which is some recording. And from this recording, you'd get a sequence of features. And this sequence of features is going to go into a neural net, which produces an output of yes or no. So this is how you would do it if you were to do this naively. So if I gave you this word, does this signal contain the word welcome? The obvious thing would be to first extract some features from it, maybe a spectrogram, and then construct an MLP, which looks at the entire spectrogram and takes a decision. What could be a problem with a setup of this kind here? Anyone? What could be a problem with a setup of this kind? So actually, this is the trivial solution, right? Train an MLP for the entire recording. So would a network that has been trained in this manner, so if the network were trained to recognize the word welcome when it occurs in the beginning of the recording, would it also recognize the word if it occurred later in the recording? Yes or no? Why not?
Because it's not present in the training data.
It's there in the training. It's there in the training data. It's just in a different position, right? So if you were to look at the recording as a vector, in the first case, the pattern is occurring in these components. In the second case, the pattern is occurring in these components. They are living in entirely different subspaces. Different components are being activated. So if I want to find a wake-up word, what I really want is a network that's going to fire, that's going to output a yes, regardless of whether the word welcome occurred earlier in the recording or later in the recording. Similarly, if I were to build a network to identify pictures with flowers, then the naive thing is, just begin with lots of pictures with flowers in them and put the whole thing through an MLP, and it's going to output a yes or a no. So if I were to do this, and we can actually do this with the MNIST digit classifier, and does a pretty good job. You'd get a 98% accuracy if you did that. But if I were to do that, then would a network that's been trained to detect flowers when they occur in the top left corner of the image also output a yes if the flower were to occur in the bottom right? Would it?
No.
And yet again, why?
Because it's not position invariant.
This is now because the second picture lives in a completely different space than the first one does. A different set of components are being activated, right? So once again, we need a network that will fire regardless of the precise location of the target object. So we have this kind of situation. In many problems, the location of the pattern is not important. Only the presence of the pattern is important, but conventional MLPs are sensitive to the location of the pattern. Just moving the entire pattern by one component is going to end up with an input that lives in a completely different subspace. So if I had a three-dimensional input, and in one case the pattern occurs in the feature X, in the second case the same pattern occurs, but now in the feature Y. They are different subspaces, different coordinate axes. So if you recognize something along X, it doesn't mean anything about what you can do along Y. Whereas what we really want is something that is position invariant. So how would you deal with this? Any suggestions? Yeah.
Like a bunch of times on lots of, and this I know it's not possible to work out, but like make a classifier for like the run it on all of the windows.
Thank you, right? You can scan. So what I can do is to train a classifier which looks at a section of the input that is roughly the length of the word welcome. And then I can analyze every segment of the input for the word welcome. And what will this output here? It's going to give me an output for every single location, right? But the original question I asked was, does this recording contain the word welcome? How am I going to derive that from this collection of outputs? I don't want the output for a single segment. I want the output for at the level of the recording. So how would I do this? Would adding do the job? Anyone? Yeah. What would the MLP be doing? Someone, right? I mean, this is easy, right? Sarvesh, do you have any idea? Miguel?
Are you saying you do like an OR operator across?
Exactly, I need an OR operator, right? And what would an OR operator look like? It's just going to be a max. So here's the thing. If I have a single, if the word welcome has occurred at any single location, then that location is going to output something close to 1. And so if I just look at the largest output, if it's close to 1, then I know that the word welcome has occurred somewhere in the recording. And of course, I can do fancier things like add a perceptron, as Theo mentioned, or an entire MLP, as some of you have mentioned. But the eventual thing is you're performing an OR, and an OR is just a max operation, right? So this is how you do it. And so here's what you do. You'd be scanning left to right. And at each position, you're going to be looking at a section of the input. And you'd pass the section of the input through an MLP. So you're going to get a collection of outputs, one per position. And then you can take a max or a soft max of the entire collection that comes out. And this is going to be position invariant, right? But then if I look at it this way, the whole thing is just one giant network. Because remember, the max, soft max, all of these are standard perceptrons. And so I had an output at every single position. And all of these outputs were passed through a downstream perceptron or MLP to get my final output. So this entire thing is just one giant network with one minor modification. At the lower layers, I have many subnets. And all of these subnets are identical. So it's a large network where the lower layer networks are all shared. They're common. It's a shared parameter network. And the entire network is shift invariant. If the position of the pattern moves, the output does not change. Make sense? Questions? Anyone? So Vinayak's got a question mark on his face. Any question? No? Okay. All right. So this entire thing is just one giant MLP, where the final soft max is the final output layer. I can just write giant MLP, and I'm done with it, right? So same thing with images. If I want to find out if there is an image, if there's a flower in this image, then I would start off with a flower size MLP and then scan the entire input with this flower sized MLP. And I'm going to get one output for every position of, once I scan it, I'm going to get one output for every position that I have analyzed. And then I could put the collection through a max, a soft max, or an MLP, and that's going to give me a final decision on whether the image has a flower or not. So once again, if I look at it, this is what I'd be doing. I'd be scanning left to right, top to bottom. At each position, I pull out a little segment. I put it through my MLP. I get a collection of outputs, one per position. Put the collection of outputs through a max or a soft max or an MLP, and that's my final decision. But then the whole thing is just one giant network, exactly as before, with one minor modification, that at the lower layers, I have a collection of subnets, which are identical. Basically, the same network is looking at every position. So these are all subnets with identical parameters, which are analyzing different positions of the input. So once again, this whole thing is just one large giant network where the final soft max is the output layer. And I could have just written giant MLP, right? Well, Okay, I think we've had enough time for this. Does anybody want to answer the first question? So let me pick on this person here, Rishikesh. The first one's true. And what about you? How about the second one? Also true, right? So we can determine if the picture has a flower by scanning it for a flower with an MLP, scanning for a flower to determine if the picture has, scanning a picture for a flower to determine if the picture has a flower in it is strictly the same as analyzing the entire picture with one large, giant shared parameter MLP. What do I mean by a shared parameter MLP? Anybody? So, kind of. Can we be more specific?
The initial layers are shared between.
So at the lower layers, we have put a constraint that all of these subnets are identical. They have exactly the same parameters. And this is an externally imposed constraint. It's not something that just automatically got learned. We said this scan subnet is the same as this subnet is the same as this subnet. By imposing this constraint, we're forcing them to share parameters. So it's a shared parameter MLP. Now, before I continue, I'm going to introduce a little change in how I visualize things. So far, I've been showing an input of this kind. If I was scanning across time, then the x-axis here is time. I have an MLP, which is looking at some section of the input, and then it's scanning left to right as it goes forward like this. But then if I drew an MLP in this manner, there's a, visually there's a bit of an oddity. It just gives you the impression that this yellow neuron follows the orange neuron in time, whereas it doesn't. That entire network applies all at once at that location. And so the correct way to visualize it is something like this, where all of this entire operation occurs at just one instant of time. And so the inputs go into this layer, which has 3 neurons. The outputs of this layer go into this layer, and so on. So in order to ensure that we don't get the wrong impression when I draw these pictures, I'm going to draw my networks in this vertical manner to convey the right image. This clear to everybody? Yeah, okay. So I can simplify this further and not draw all of the arrows. I'm just going to draw it like so, where if I have an arrow of this kind, it means that this layer is fully connected with this layer. Every neuron in the lower layer is connected to every neuron in the upper layer, okay? And sometimes I might completely eliminate the little circles. You just have to be aware that these are layers connecting to other layers. And so this network is going to actually look like this. This is a full shared parameter network, but this is the same as scanning with one column, where when I'm scanning, I'm stepping by 2 inputs at a time. So that's my stride. And the collection of outputs is finally being passed through the decision layer on the top. So this is a single MLP. It's a shared parameter MLP. It's also scanning with an MLP. That clear to everybody? Many different interpretations of the same thing. So let's be very comfortable with this picture and this notion of scanning with an MLP and how parameters are shared, because this is going to appear in your quiz, and you're going to have many doubts if you don't understand this just right.
Can you explain why the stride is 2 if there's 3 neurons? I mean, why wouldn't we just...
So that's exactly, the point is this. This stride could have been 1, right? I could have had all 3 of these guys just look at this one.
Right.
In this case, it just happened to be looking at a width of 2 time instants.
So that's just we decided.
That's just completely arbitrary, right? And I put that there just specifically to convey the idea that these 2 are different things. The width of the input that it's looking at has nothing to do with the number of neurons on the layer itself, right? So here's one with a stride of 1. And then that's what it would look like, to answer your question, right? So again, it's looking at 2 inputs, but it's striding by 1. They're 2 very different things. This picture clear to everybody? How it's looking at 2 inputs, but striding by 1? Yeah, okay. So how do I train these networks? Firstly, what is the earthly benefit of having this, scanning and putting the whole thing through an OR? Can anyone tell me? Yeah. Way fewer parameters. There's a much, much bigger benefit to this. Can someone give me an idea? Why would I do this? We'll get to that. Way fewer parameters is indeed a big deal. Yes?
So there's a better generalization since...
Better generalization, Shrey, you? You're able to get the smaller parts.
Irrespective of location.
Irrespective of location. That is the correct answer here. But there's something bigger than that, right? Suppose, let's go back and look at this. If I wanted to train this explicitly, how am I going to train it? go back here. If I want to train this explicitly, how am I going to train it? I'm going to have to find boxes which surround flowers. And I'm going to have to mark every section saying this has a flower or not, right? We started off saying I have a box flower-sized MLP that can detect flowers. How do you train such an MLP? You're going to have to give it lots and lots of flower-sized images, some with flowers, some without flowers, yes or no. This has a flower and this doesn't, and then train the model, right? And who's going to actually be sitting there marking out individual flowers in every single picture that you've got on the web? Nobody, right? Whereas if I do something of this kind, or I can just say, here is a picture, somewhere in this there's a flower. I don't have to specify the location of the flower during training. And so this is a much, much bigger deal than just shared parameters and everything else. The ease of representation and labeling of the data itself. That makes sense to everybody, right? And so that's that, yeah.
It's only useful for specific tasks, right? If you want to identify the location of a particular then we'd have to specify the.
In that case, yes, we'll get to that, right? But most generic thing, how often do you actually want to identify the location? Now, here's something else, right? So this is very pretty. And I'm being slower than I should, but maybe I'll speed through other things. What did we eventually learn at the end of this? So first, how do you learn such a network? To see how I learn such a network, I've got to consider the fact that these are shared parameter networks. All lower layer networks, subnets are identical. They're all searching for the same pattern, which means when I'm performing back propagation and gradient descent updates, if I find gradients coming up to this column of the network, and if I update the parameters here, I must reflect those updates into every copy of that column. So how does that work? When I have shared parameter networks, I basically decree just by by fiat that these two guys are going to have the same parameter, for instance. This is just me saying these two are going to have the same parameters. Then when I actually construct the network, here's what I have. I have two completely separate weights, but they are restricted to having the same value. So when I draw the influence for this one, so any training, for any training instance X, perturbing this guy will perturb the divergence. So I can update it, but that must be reflected here also. How do I do that? Here's what the influence picture looks like. The two weights have a common shared value WS. So perturbing WS perturbs both those weights, perturbing either of those weights perturbs the output, right? When I'm learning, what am I trying to learn? I'm not trying to learn the individual weights. They have a shared common value. So I am actually trying to learn the shared common value WS. And so if I were to write down the derivative of the divergence with respect to WS, what's that going to be? Again, here is what I had, right? I had the divergence. I had W1, I had W2, but then both of them have the common value WS. So what is the derivative of the divergence with respect to WS?
The sum of all the derivatives.
I'd have to sum over both paths, correct? And so this is going to be over dW1 times dW1 over dWS plus d divergence over dW2 times dW2 over dWS. And what is this guy here?
One.
That is 1. I'm just copying the value over, right? And so also this term here is also just 1. And so the derivative of the divergence with respect to this common shared parameter is the sum of the derivatives of the divergence with respect to every individual weight that was required to have the same common value. And each of those derivatives can be computed using backprop. Now here's the beauty of the whole thing. In so doing, I have managed to train this entire network. But I trained the network without actually ever marking the location of an individual flower. What did I eventually learn though?
Unrecommended flower.
Can you say that loud?
I said how to recognize a flower.
Not just that, I learned the MLPs that recognize the individual boxes. Without ever giving my model the location of a flower, I have implicitly learned a model that can find out the precise location of a flower. That sound magical to you guys? Because basically what I have done is I have also trained this network. And that network, what does that network do? It tells me where the flower is. So, questions? Yes?
How did it learn whether to detect a flower or not without actually labeling the data itself?
Because the only label I gave it was the label at the final output. Yes or no, does this large image have a flower or not? And the gradients were passed backward and all the parameters were trained, right? In training the parameter, you train the parameters of the individual subnet also. And what does the individual subnet do?
Detects a flower at a grid.
Yeah, yeah.
But how does the individual subnet know that this particular, the flower is located at this place? Or let's say there was a
The individual
next-
subnet is looking, the way I've drawn it, the individual subnet is looking at a specific portion of the input, so it knows. Period, right? Yeah. Yeah.
So when you are calculating the gradients of divergence with respect to WS, there is no WS if I don't make mistakes. There's something that as a condition that W1 and W2 are equal. So how that backpropagation influence the updating of the W1 and W2?
So the backpropagation updates WS, which gets copied to W1 and W2.
So then there is some WS. I mean,
And they have the same value, so, right? Yeah.
Does the size of the flower matter?
So in this naive discussion, so long as the lower subnet is looking at the size of the, something approximately the size of a flower, you should get it. But yeah, I'm assuming over here that the lowest subnet knows the size of the flower. Anyway, let me continue because before we get dragged too far down this, right? So any other questions? So here, for more generally, if I have something of this kind, I have a bunch of edges which are supposed to have the same common value. So the derivative of the divergence with respect to the common value is going to be the sum, not the average, but the sum of the derivatives of the divergence with respect to the individual terms that that share that value. And so that's what I could just stick in, right? If I'm training a neural network, a shared parameter network, I'd initialize all the weights. I want to compute the derivative of the loss with respect to the common value for each subset of weights that are supposed to share a particular value. For example, all the red edges over here should have the same value, so they will have one WS. These blue edges will have the same value, so they'll have a different WS. And so I need a derivative with respect to those guys. And so that's this term here, which is going to be, the sum of the derivatives of the divergence with respect to each of the individual weights that share that common value, and that's what I would stick into my gradient update, right? So, and that one is computed using backprop. Questions? Okay, so let me go ahead, right? The story so far, position invariant pattern classification can be performed by scanning. 1D scanning for sound, we saw that. 2D scanning for images, you can have 3D scans for higher dimensional data. Scanning is equivalent to composing one large network with repeating subnets. So the large network has shared subnets. Learning is performed using backpropagation rules that are modified to combine gradients from parameters that share the same common value, right? Okay, so, but then let's take a slightly different look. I'm just using this vertical figure as before, right? And so when I'm analyzing this input, at each location, each layer of the network is computing a bunch of outputs. Every neuron in the layer is computing a bunch of outputs. So the first layer might be computing these 4 guys. The second layer neurons are going to be reading those 4 values and computing their own 2 values. And the third layer is going to be computing its own value from the outputs of the second layer. And this set of values is computed at every single location that you're scanning. And the final outputs are, of course, put through the softmax or max. This was the computation we were performing. Everybody clear with this, right? You lady there, can you turn your phone upside down, please? Can you turn the phone upside down? Is that a phone? Yeah, thank you. Right. So we don't want, I mean, my apologies, but I don't like phones. Yeah. So here. So let me do things differently, right? So instead of just having the entire network compute its outputs at each location, let's say that layer 1 is in a hurry. It computes its position values at the first position, doesn't wait for the second layer, and just goes ahead and runs off and computes its outputs everywhere. Then at the first location, the subsequent layers read the outputs of the first layer neurons and compute their outputs. Will the final output be different at this location? Yes or no? Can we hear a combined no? Right? Cannot be, right? I'm using the same values. So same thing. So the output here does not change due to the reordered computation. Same thing. Now I can have the second layer neurons not wait for the third layer and compute their outputs through the network. And then the third layer neurons take the outputs of the second layer and compute their output at the first position. Will the output now be different? No. Can I hear a no? No. Thank you, right? I need to, so the next time I need that corner of the room to also say no. Okay. And now the third layer can go off and perform its computation. And nothing changed, right? So all we did was reorder the computation. And we know that this will not change the output. So if I were to look at it from the perspective of pseudocode, earlier here's what we were doing. At each location, we were pulling out a segment and passing it through the entire MLP. If I were to expand the MLP, this is what you were doing. At each position, you were pulling out a segment. That segment was then put through the layers of the MLP. And so here is the key bit. The first layer of the MLP alone looked at the entire width of the input, right? So if I were to draw this, I had some inputs, and the first layer of the MLP looked at maybe many vectors, each of which could have its own dimension. But then subsequent layers only looked at the output of this layer. So I need a special if clause for the first layer to consider to read in this span of input. But subsequent layers just look at one position, right? And then at each layer, I'm just computing an affine value from the outputs of the previous layer and putting it through an activation. But now observe that all of the operations are happening inside the second loop, inside the layer loop, right? So if I were to, so the first loop is over time, the second loop is over layers. Now, if I were to flip these two indices, would the final output of this computation change? No, because all that happened was I just changed the order in which I was doing things, but the final output shouldn't change, right? Because they don't interact. And so that gives me this pseudocode. I'm going through the layers in the outer loop, and within each layer, I'm going over time. And the result must be the same. So this is what we have done, right? Same thing for a two-dimensional input. So in a two-dimensional input, what we were doing earlier was scanning the entire input with an MLP, and then putting the whole thing through a softmax. And so the input layer is just sections of the image. They're going through the MLP, and the MLP is computing one output at each position, like so. And so I've arranged the outputs of the MLP in the same order, in the same arrangement as the input image itself, to show you the one-to-one correspondence between each dot at the output and a corresponding location in the input. And that final thing is put through the softmax, right? So instead, let's say the first neuron of the first layer of the MLP went off and performed its computation, like so, scanning the input without worrying about its neighbors and friends. And then the rest of the neurons did their job. Would the final output be any different? It should not be, right? Same as before. And so In fact, you wouldn't be doing this with just one neuron, you'd be doing this with all 4 neurons. So the first layer neurons are all going to be looking at each position and drawing their outputs, right? And so when the first layer is done, I'm going to have 4 maps, 1 per neuron, indicating the output of that neuron at each position in the input image. And now I have the image, original image. I have my first layer neurons, let's say 3 of them, which have generated their little outputs. But then my network itself has, let's say in my example, a couple of other neurons later, which are fed by the first layer neurons. And if I want to compute the output of the network for this block, what would I do? Anybody? What would I do? So here's what. This neuron has analyzed the entire input and generated these dots, right? So this block corresponds to this dot for this guy, right? And maybe this dot for this guy, and this dot for this guy. And so I could just feed these 3 things into my second layer neurons, which would go into my third layer neuron, and that output should tell me whether there's a flower or not in that particular block of the image. Make sense to everybody? Yes or no, right? Okay, so easy. So I just have to pick, if I want to analyze any specific location of the image, I just have to pick the corresponding blocks, the corresponding outputs from the maps generated by the first layer neurons and pass them through the network. And now the second layer neurons can do the same job. They can begin generating their outputs for each position of the input without waiting for the third layer neurons. And so if they did that, the second layer neurons, now observe this. The second layer neuron is actually looking at, for each position, the second layer neuron is looking at 1 dot from each of the maps produced by the first layer neurons. So now the second layer neurons are going to be jointly scanning the outputs of the first layer neurons. And now if I want to find out if there's a flower in that central box, I just have to read these dots from the maps generated by the second layer neurons and look through it and analyze it. Done. And of course, the third layer neuron can also now go ahead and scan the outputs of the second layer neurons in unison. And finally, the map generated by the output neuron is going to give you the outputs at each location, which can be put through the softmax. That clear to everybody? Right. So once again, and so if I want to know what happened in any specific location, I just read that the value at that location in the map generated by the third layer neuron. And that, of course, can be put through the softmax. So, or we do something, typically what we do is flatten the outputs generated by the final layer and put them through a softmax. But that's kind of a bit besides the point. So here is what happened. Earlier, we were scanning the input along X and Y, pulling out a segment, and then analyzing that segment using the entire MLP to generate one value at every position. And that value was put through the final softmax. And if I look at this again, I was going through the input, scanning the input. At each location, I was pulling out a segment. And observe again that only so when I was doing this for the image, I had an image. At each location, the first layer and the first layer alone looked at the entire block. And then the subsequent layers only looked at the output of the previous layers. That's how we did the computation, right? And so this is what we are doing here. For the first layer, we are pulling out a section of the input. And then for every other layer, we're just operating on the output of the previous layer. We first compute an affine term and then put that affine term through an activation function. And then once again, observe that all of the action is happening inside the innermost loop, which means that if I flip the order of the loops, so I push the layers up on top, and the scanning inside, the final output should not change. And so that's basically what we are doing. So if I were to do this in vector notation, yeah, this is what it is. Right? My slides are kind of, yeah. We're going through the layers. Each layer is scanning. The first layer alone is looking at a section of the input, but each layer is scanning the outputs of the combined outputs of the previous layer neurons to generate its own output. Okay. So the story so far: position invariant pattern classification can be performed by scanning the input for a target pattern, which is equivalent to composing a large network with shared parameters. The operations in scanning can be equivalently reordered as scanning the input with individual neurons in the first layer to produce scanned maps of the input, and then jointly scanning the map of outputs by all the neurons in the previous layer to generate the outputs of subsequent layers. So here's the poem. So there's a question on Zoom, somebody asked it here, if the size of the flower matters. Again, in the naive mechanism that I just described, then the lowermost subnet is assumed to know the approximate size of the flower. We'll see how we can get around that. Okay, guys on Zoom, you're going to be answering this question. Not able to read the poll?
Not able to select options.
Okay, that's...
It's already done.
Maybe, okay. Try again, guys. That gave you plenty of time to read the question, so. Okay, someone on Zoom, do you want to answer the first question?
Be
True or
true.
false? Okay, and the second one?
It's true as well.
True as well. So let's take a look. Scanning an input with an MLP is mathematically equivalent to first scanning it with the individual neurons in the first hidden layer and scanning the output maps of the first layer with the rest of the network. True, right? And the operation can be recursed. Scanning the output maps of the first layer with the rest of the network is equivalent to scanning the first layer map with the second layer and then scanning the second layer maps of the remaining network. So basically all we are saying is I can change the order of scanning and then going through the layers to going through the layers and scanning with each layer. And the final output is going to be the same in both cases. But then magically what happened is that we suddenly went from just scanning with an MLP to a structure that we all know as the convolutional neural network. Right? So, but then let's go back and look at what happens. What do the neurons and the individual layers do? The way I defined it right now, the task of looking for a flower-sized pattern, which layer does that job? The first layer, because the first layer is the one that's looking at a flower-sized region of the input. The subsequent layers are just looking at the outputs of individual neurons in the previous layer. And so the entire MLP looks for a flower-sized pattern, but then the fact is that it's only the first layer that's looking for flower-sized patterns, things that look like a combination of sepals, flower petals, and maybe leaves or whatever else, right? And then subsequent layers are just going to determine if the flower-sized patterns that are detected by the first layer neurons could technically combine to give you something that looks like a flower. So the entire onus of finding the appropriately sized patterns is on the first layer neurons. Right, so the first layer neuron is responsible for evaluating the entire window of pixels. Subsequent layers only look at single pixels in their input maps. Let's do this differently. That's too much responsibility for one layer. We know that overburdening individuals with too many responsibilities is a bad thing to do. So Let's share the responsibility, right? I'm going to make the first layer neurons look for smaller patterns. Maybe things like the sizes of individual petals, individual sepals, stamens, things like that. And so now the first layer neurons are looking at smaller blocks. And they're going to scan the input using this smaller block. And so here is what happened. The first layer neurons scan the input, and they scan the input with maybe a box of this size. And so I have, say, 3 neurons, and they generated their maps. Again, remember that these maps are individual dots, right? One from each position. But then what I really want to do is to look for flower-sized patterns. And flowers are not this small, right? So let's say the flower is this sized, into which I could fit four of these guys. How can I compose a flower-sized pattern when the neurons of the first layer are looking at things smaller than flowers? How can I do that?
We look at parts that make up a flower.
So, somebody on Zoom, you answered me. Please, can you complete the answer?
Use more windows, like
I can actually look at 4 of these guys over here at the same time, right? And so when I look at these four, I'm effectively looking at the outputs of this neuron at 4 different locations, which is now the size of a flower. So instead of looking at individual dots, individual outputs, at the outputs of the first layer neuron, I begin looking at windows of outputs. That makes sense to everybody? Right? And now, if I look at the second layer neuron, which is looking at these windows, how many different elements is the second layer neuron considering in this example? 3? How many would it be considering? 1. Can somebody give me a better answer? There would be 12, correct? Because this second layer neuron is looking at all of these windows. So it's going to be looking at this guy, and 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 this, and this. So the second layer neuron is actually looking at 12 distinct inputs because it's looking at a 2x2 window in the outputs of each of the 3 first layer neurons in my example. That make sense to everybody? You guys on Zoom, did that make sense? Yes, no?
Yes,
Yeah, okay. Someone reply, because you're representing the entire collection on Zoom. And so, yeah.
I don't understand this. Could you come again with that, please?
Okay, so here is going back to my example. Thank you for asking. So we said that if the first layer neuron only looks at blocks this sized, and if I really want to look for flowers which are the bigger size, which I'm drawing on the board, then I'm going to have to look at 4 of the smaller blocks to compose a flower, right? Which means I'm going to have to look at 4 outputs from each of the first layer neurons to compose a flower. And there are 3 first layer neurons in the example I drew on the board. I'm looking at 4 outputs from each of the 3 first layer neurons. So that's a total of 12. Did that answer your question? Yeah.
Yes, does. Although I'm seeing 4.
You're seeing 4, but you're seeing 4 here from the first layer neuron, the first neuron, 4 from the second, and 4 from the third, my example. Let's look at the slide. The slide is a little more explicit. Here, I have, if I want to look at something the size of a flower, then I'm going to be looking at 3x3, a 3x3 section from each of the output maps of each of the neurons in the first layer in order to compose something the size of a flower. So each of the second layer neurons is looking at every portion of the input that was considered in computing any of these 9 dots, right? So and those 9 dots came from the 9 little boxes within the dotted region, which means that by looking at those, by collectively looking at these 4 windows, each of the second layer neurons is actually looking at this larger region of the input. But then once again, if you look at all the values being considered by the second layer neuron, it's looking at 4 maps. Within each of the 4 maps, there are 9 highlighted yellow dots, each of which was individually computed. And so the second layer neuron is actually looking at how many values are there in this example?
36.
9 times 4, 36. That answer your question, guys on Zoom? Did that make it? Okay, Sarvesh?
Yeah, so in this case it's 9, but in other image case it might be more.
This is just my illustrative example, right? So in the homework that you will do, you'll actually look at smaller regions.
How can we generalize? Because this 9 tiles cannot be same for every other image. Because it carries 4 for one, 5 for other.
No, this is the size of the approximate size of the flower you're looking at over here, right? So which is going to be, you're looking at, so the first layer neurons are looking at small subsections. You can think of, this is what you're going to look at for small regions of the image. And so I'd need to compose something which is, again, I'm assuming a priori knowledge when I explain it this way, but if I recurse it, that's no longer required, okay? And so this is going to give me something that's approximately this size. And I raise an interesting question. I don't know if I'll be answering it in today's class, but this will come back, okay? And so what you will learn, for example, here is, so each of the first layer neurons is looking for a different kind of pattern. So the first neuron will be looking at flowers, petals that are standing up. The second layer neurons may be looking for things that look like the stamens in the middle, right? The second neuron in the first layer. So you might have this neuron, say, looking for petals which are on the upper edge. These guys may be looking for stuff in the middle. And these guys might be looking for, petals which are angled this way. And so the second layer neurons are going to learn that if I find that this neuron fires in the first 2 positions, and this neuron fires in the top right, and this neuron fires in the middle, and this neuron fires in the bottom right, then this is probably some substructure of a flower. So again, it's looking for patterns in the output maps generated by the first layer neurons, right? And of course, the second layer neurons are going to be scanning the output maps of the first layer neurons, but now jointly. You're looking at all the maps of the first layer neurons together to compute your output. And now, if I want to know if there's a flower in the top left corner, I just have to look at the top left element of the maps generated by the second layer neurons to analyze it for a flower, right? And so my output, my third layer neuron is now going to be jointly scanning the output maps of the second layer neurons for just one dot at a time. But then I don't have to stay with this, right? Again, I want you to remember that this, in spite of this very fancy distribution of parameters, it's still a shared parameter network. Why so? So if I look at this guy, each of these 9 dots was computed using the same neuron. So it's like having 9 values obtained from a different location of the input, but those 9 values were computed using the same parameters. Similarly, in this map, each of these 9 dots were computed using the same neuron. So I'm getting 9 values, each computed using the same set of parameters. And so also for the third set of dots. So the second layer neuron is actually now looking at these. In my example, now there are only suddenly only 27 inputs. Again, I have to fit, like, there's only so much I can fit on my slide. But you get the idea. By the time I get to the second layer neuron, I'm looking at a flower-sized window. But this network, the MLP that's looking at a flower-sized window, is a shared parameter network itself. So earlier, the network that was looking at the entire input was a shared parameter network. Now, even the subnets within it are shared parameter networks. But overall, the entire structure remains a shared parameter network. It's still the same as scanning the input with an MLP, with the additional constraint that the MLP that's scanning the input itself shares other parameters. Okay? So, and now I can recurse this logic. The first layer neurons could be looking at something much smaller. The second layer neurons could be looking at windows in the maps generated by the first layer neurons. And so now the second layer neurons are looking at a slightly bigger region of the input. And the third layer neurons could be looking at windows in the maps generated by second layer neurons. And now the third layer neurons are going to be looking at a much larger, when the third layer neurons looks at these windows in the maps generated by the second layer neurons, they're effectively looking at any region in this map that was used in computing any of these 4 values, which is the region shown by the shaded red region, red box. And so that in turn means that it's analyzing any region of the input that was used in computing the elements within the shaded red box. And so that's going to be the entire window of the input. So I just distributed the parameters across the network across 3 layers. But regardless, and I can keep doing this, right? So how did this change my pseudocode? Right. So regardless of how I do it, regardless of how many layers I distribute this over, I'm still scanning the input with an MLP. The only thing that happened was that within each layer of this MLP, I have additional shared parameters. And so the entire thing is still just the same as scanning the input with a shared parameter network. And if this is not entirely clear, then I have a write-up that's going to be posted on Piazza, and you're going to deal with this in your quiz and your homework. So by the time we are done with you, you will understand or get poor marks. Okay. So how does this change my pseudocode? Now, earlier again, if I was just scanning with an MLP or scanning over the inputs, scanning the input, pulling out a window, flower-sized window, and then analyzing it with my MLP. And then when we redid that, we said, here's what we look like. We are scanning through the layers, but then each layer scanned the input. And when it scanned the input, the first layer alone had a special if clause. It was pulling out a segment of the input. For the other layers, it was just directly reading the outputs of the previous layer, one position from the output of the previous layer. It turns out that when you distribute things in this manner, the pseudocode actually, you'd have thought it would get more complex. It actually gets simplified, because every layer is now reading a little window from the output maps of the previous layer, and then collectively using those to compute an affine term, and then at an actual value by putting the affine term through an activation. Any questions? Yes?
Assuming that the window size is the same.
No, so again, if you look at the code, there's a window size. I have the subscript here, which indicates that the window sizes can be different from layer to layer. Nothing changed, right? Yeah, any questions? Any questions on Zoom? Okay. All right. So this business of scanning with a window, this is what is called a convolution, which is why this is called a convolutional neural network. Okay. Again, I want you to remember that the basic premise that we began with has never been violated. We were looking for flowers. We wanted this to be position invariant. So we came up with an idea of what the size of a flower could be. We built an MLP and scanned the input with that MLP, and then took an OR over the collection of outputs. And we had additional ways of distributing parameters through the MLP, but it's still scanning with an MLP. It just happens to be a shared parameter MLP, right? So most should occur. And so here's what it would look like. The first layer is going to be looking over a section. If the way we had originally done it, if you wanted to look for a welcome-sized region of the input, the entire MLP would be looking at a welcome-sized section of the input. But now, if I want to do this with a distributed network, the first layer would be looking at a smaller section of the input. The second layer is going to be looking at, a window in the outputs of the first layer. And so now it's going to be looking at a larger window of the input. And the third layer is again going to be looking at a window of the output of the second layer, and so looking at an even bigger region of the input. So when I do this, when I scan this across when we saw the image pictures where I was scanning for a flower, I was looking at two-dimensional input. That's what is traditionally known as a convolutional neural network. This too is a convolutional neural network. You just happen to be scanning in just one direction across time. And so this can be called a 1D CNN or also called a time delay neural network. Just terminology that you must be familiar with, okay? So this is what it will look like, right? And then of course you can put the final output through a softmax or an MLP or what have you. So this is a time delay neural network. Any questions so far? Questions? Okay, so she won. Is the first statement true? No? Okay. Samuel, what about the second one?
True.
Second one's true. And you are Heejun. Yes, what about the third one? True. And what about the fourth one? Oh, sorry, I got some chalk on your shirt. I'm very sorry. Okay, let's look at that. So non-distributed scanning does not require the output maps to be arranged in the same shape as the input because you're just looking at things one element at a time. You only need to make those, arrange them in the same manner as the input when you look at windows. Non-distributed scanning does not require the outputs to be arranged in the same shape. Distributed one does require it to be arranged in the same shape as the input. So far so good. Any questions? No, okay. Now, why bother with distribution? Why do we even distribute? What do we gain from this? There's several things we gain, right? So this is on top of the fact that you're scanning. We already saw why scanning and putting it through an OR is useful. And why was that useful? Pardon me?
Makes the neural network shift invariant.
There was something else I'd mentioned. Guys, you can't have forgotten in just 60 minutes. So the training data doesn't have to have the locations marked. That was the key piece, right? I could just scan, put it through an OR, and the network magically learns to detect flowers regardless of where the data flower is. Whereas if you were not scanning, then you'd need exactly flower-sized images that you are inputting to make sure that you know the image had just exactly a flower or not. Everybody with me in that, right? So, but there are other benefits now. What we are talking about now is what we gain in addition through distribution. And so, first, distribution forces hierarchical representations with localized patterns, which makes it more generalizable. Fewer computations because you have reusable parameters and fewer number of parameters. So let's look at the first thing. Remember when we were doing the multiple polygons? You didn't try to compose the individual polygons all at once. You broke it down. The first layer neurons got the edges of the individual polygons. The second layer neurons got the individual polygons. The third layer neurons then composed the larger structure. When you distribute things in this manner, you found that you were able to generalize much better and needed much smaller networks. So you really want to encourage such hierarchical learning because it ends up giving you more generalizable models. So this is one big reason why we want to enforce distribution of the parameters through the network and not have the first layer neurons be responsible for the entire flower. Number one. Second is computations and parameters. And to see this, let me use an example over here. I'm going to use a 1D scan where I'm using this vertical illustration, and I'm assuming that the first layer is looking at 8 input vectors, but each vector is d-dimensional. So if I have something of this kind, then let's say I'm looking at, this is my input, and if my first layer looks at 8 of these guys and has n1 neurons, how many parameters does my first layer require? Anyone?
8.
8? 8 into 8, so there are 8D inputs, correct? And I have n1 neurons. So how many parameters does my first layer require?
Oh, N1.
And just n1? There are 8 here, right? So how many does it require? One last try before I give you the answer. And if 8 and 1. Am I missing something?
Multiplied by d.
Times d, correct? So guys, anytime I answer a question that I pose, it means I'm collectively smarter than the 300 of you. Don't let that be true. Okay. So suppose these n1 neurons feed n2 neurons. How many neurons does how many parameters does the second layer require?
n2 times n1.
n1 times n2, right? And if these feed another layer, say with n3 neurons, how many neurons parameters do I require?
n2 times
3 times N2.
n2 times n3, right? So you get the number of parameters over here. This is what you get. So if I'm scanning the input without distribution, and let's assume I have a stride of say 2 over here, then this is what I'd be doing, the computation, right? And the number of parameters I require, I've got rid of the dots, the little circles, just to simplify the illustration. But if I have n1, n2, and n3 neurons, that's how many parameters I'm going to require. In general, if the input is k wide, then it's going to be k times d times n1 plus n2 plus n2, n3, right? Easy. Or L, as I've written over here. Now, let me distribute this, okay? Yes? If each of these vectors is d-dimensional, so then this block has 8D values, correct? Each of those feeds is feeding n1 neurons. That clarify? Okay. So now, let me look at distributing this. So when I'm distributing this, I have a neuron, I have the first layer, which is looking at only a width of 2. And it's scanning the input with a width of 2. The second layer is looking at 4 of these guys all at once. Okay? So if I do so, what is the effective input that the network is looking at, and input width that the network is looking at? Guys, 8, correct? Can everybody say 8? 8. Please answer me, guys. I don't want you falling asleep 15 minutes before the class is done, okay? So now here, I'm running behind, so now if I have this one, each of these is looking at, let's say each of these has n1 neurons, then how many parameters does the first layer require? Assuming I'm scanning, how many parameters does the first layer require?
N1,
the first layer is just going to require 2 n1, 2d n1, right? And then if I have n2 over here, which is looking at all 4, how many neurons parameters does the second layer require? And pardon me? 4 n1, n2, correct? So now let's compare these two. If I want the same number of neurons in both cases, this cannot be N1 anymore, right? This has to be 4N1, right? So if I were doing this, how many parameters does this require? This is going to require 32 N1D plus 4 N1 N2. Do you see the difference in the number of parameters? Everybody see how the number of parameters is hugely different, right? So in general, this guy is going to require 2D N1 plus 4 N1 N2 plus N2 N3 parameters when I distribute it. Whereas if I didn't distribute it, I'm going to require what? 32D N1 plus 4 N1 N2. So the first layer just blows up. This would be, right? 32 versus 8, it's a factor of 4. Now let's do the same thing when I distribute this across 3 layers. So this is what the scan would be like, right? Now, there's something else that happens over here. If I look at this, when I'm scanning the input, then are there any computations that are performed when I'm scanning the first position that I can reuse at the second position? Which ones? Second and third, right? So if I do this over here, I can actually reuse these 3 guys. Second, third, and fourth. So which means suddenly I also am performing fewer computations because I'm reusing the computations at each position, right? So now let me distribute this over 3 layers. If I distribute this over 3 layers, then how many parameters do I require in the first layer? Just going back there. Can someone tell me? How many parameters would I require in the first layer? It's still going to be 2D and 1, right? Nothing changed for the first layer neurons. It's looking at 2 inputs. Each of them has dimension D. There are N1 neurons. What about the second layer?
2 and 1.
That's going to be 2 N1 and 2. And the third layer is going to be
2 and 2 and 3.
2 and 2 and 3. Okay, now going back here, if I had a corresponding network of this kind, so this would require 4 N1 neurons, right? To maintain the same number of overall neurons, this is going to be 2 and 2. So that the second layer has the same number of neurons in both cases. And so then if I go back and work this out, how much, the first layer is going to require 32 N1D, right? And what is the second one going to require?
8 and 1.
That's going to be 4, 8, and 1, and 2. So again, compare the two. So you can see how just the further I distribute things, the fewer the number of parameters I'm going to get. Yes, Evan?
Okay, I have a question. So why exactly do we have to multiply the number of neurons in the non-distributed scans, layers? Because I thought the key was that one.
So if I'm just looking for an equivalent network in both cases with the same number of neurons. So here, the first layer effectively has 4 N1 neurons scanning an input 8 wide, correct? So here, to have the same number of neurons, this would have to have 4 N1 neurons too, that's all. Okay. So looking at this, you can see that the number of computations is greatly reduced. And once again, you can see how things get, here I was just striding by 2. So this middle guy is not, even if the second one is scanning, the gray ones are not being used in computing the first position, but they're definitely used in computing the second position, right? And once again, you can see all the things that are being reused when I'm striding by 2, right? And if I have a network of this kind, so again, the same principle holds, except that the third layer is looking at 3 consecutive inputs from the first layer. Then if you actually work this out, I won't go through the details, but if you work this out, you can see how much reuse happens from position to position. So in general, just distributing the network parameters, network is going to first give you distributed representations which are more generalizable. Secondly, it's for the same sized network, scanning the same sized input. It's going to use far fewer parameters. And computation-wise, you're going to be reusing a whole lot of compute, which makes things very, very, very efficient, right? Makes sense to everybody? Yeah, so I have some pictures and numbers for the 2D version of it on the slides. I'm going to skip that because we're out of time. But the 1D illustration must have sort of conveyed the idea fully, hopefully, to you guys, right? So why distribute? Distribution forces localized patterns in lower layers. And you can get large, sometimes orders of magnitude reduction in parameters. And gains increase as we increase the depth over which the blocks are distributed. And you get significant gains from shared computation. So the key intuition remains that regardless of the distribution, we can view the network as scanning the picture or the input with an MLP. The only difference is the manner in which parameters are shared in the MLP. And because we are sharing parameters, we need fewer parameters, and we can reuse computation, right? So story so far, just adding to what we saw. We said position invariant pattern classification can be performed by scanning for a target pattern. The operations in scanning with a full network can be reordered as scanning with the input with individual neurons in the first layer, and then jointly scanning the maps produced by the earlier layer neurons in each layer. And the scanning block can be distributed over multiple layers of the network. This results in significant reduction in the total number of parameters and the compute, right? So final poll. So folks on Zoom, this is for you. Okay, I'm going to hurry you up, guys, because we're running out of time. 5 seconds more. All right. Zoom, is the first statement true?
Yes.
Second one?
Yes.
Yes.
Third?
Yes.
And the fourth?
Yes.
Also.
Yes. All
Well, it doesn't result in reduced memory requirements. We are scanning with an MLP. Nothing changed as far as scanning with the MLP is concerned. The number of intermediate values that you're storing at each position doesn't really change. All that changes is the reduction in the number of parameters and the reduction in the amount of compute because you're reusing terms, right? Okay.
Question, Prof.
Yeah.
So if we stride it by say 4 in the example you give, you'll be using much more computational time since we are not reusing any of the neurons, but we'll be losing any information.
So if you're sliding by more than 1, yes, you are likely to lose information. Again, these are all just for illustrative purposes, right? So some final touches, terminology and shrinking the maps and accounting for jitter terminology. The region of the input that a neuron looks at, it's called, what is it called? So again, the entire operation can be redrawn as maps of the entire image. You can think of each neuron as looking for a particular pattern and redrawing the image where it highlights the specific pattern it's looking at. And so in that sense, you can think of the neurons as just repainting the image with some things highlighted. And so the second layer neuron, which actually jointly scans the maps generated by the first layer neurons, are also essentially repainting the image with some patterns highlighted. And this happens all the way till the end, right? And of course, The set of weights of the scanning neurons is often called a filter. Each filter scans scans for a pattern in the map that it operates on. And furthermore, the size of the input and the pattern of the input that each neuron is looking for is called its receptive field. Now, in the first case in the layer of the first layer neurons, the receptive field is very simple. It's just the size of the input itself, right? And the patterns, the weights, give you the pattern it's looking for. That is the receptive field. For higher layer neurons, because once you go into the higher layers, you can have ORs and ANDs. So finding out what the precise receptive field is can be quite challenging. You often have to do it by assigning, by using back propagation to determine which inputs have the greatest influence on the output. And then there's a terminology called flattening. The output of the final layer of the scanning network is often just recast as a single vector before passing on to an MLP or a softmax. So it's called flattening. Then you can actually stride. In the examples we showed striding by 2. So the length by which you move is called a stride. And if you're striding by 2, then all the maps are going to shrink by a factor of 2. If you're striding by 1, they won't shrink. We'll see more of this in the next class, right? And then one final thing, when we are beginning, once we have this kind of composition by parts, then the second layer neurons are saying something like, if there's a petal here and a sepal here and maybe a petal spacing sideways here, that's a pattern that could represent a flower. But then if this petal moves by 1 pixel, does that suddenly become not a flower? It does not, right? And so you want to have some jitter invariance. And so for this, we have things called pooling, which will look at regions of the input and then fire based on the set of values it sees. For example, if a flower is discovered anywhere in that region, if a petal is discovered anywhere in that region, it's a petal, right? So we have this pooling operation, which just picks maxes within little regions. So this is the pooling operation. We'll see more of this later. And so the overall structure, this convolutional neural network, is essentially a distributed, network that scans an input with an MLP with some additional engineering, distribution of parameters, things like pooling, and so on. And there's some decision making on how the final outputs are used to come up with the final decision. But other than that, this is the general idea. And so we'll pick up more on this in the next class, right? This is the CNN. Here's the stories of our slide. You can read it. Thank you, everybody. Yeah.
For the ADF,